to talk about basically the convergence of two lines of research that I've been working on for the past decade or so, and some of the ways those things will intersect in the new laboratory that I'm starting up here at the University of Rochester. All right, so for a while I've had this idea of high performance robot motion planning navigation that ties in language. Basically, how do you actually Oh, sorry. Okay. All right. Anyways, so motion planners that can learn from language is this idea. So right now, when we want to apply motion planning to some robot, some particular robot application, inevitably what ends up happening is they will hire the latest and greatest PhD who has done this in their graduate work, and they will apply their kind of domain expertise to this problem to be able to set up whatever constraints, cost functions, relationships, representation to effectively solve this problem for us. We see this happening all the time today. This is early. Controlling this, very complex system by, developing this very complex GUI to set up all the relationships and everything else. So would it be nice if you can just, basically talk to it like a walkie-talkie, explain to it what you want it to do, and kind of understand the explicit and implicit things you are trying to communicate to it, so it can basically solve its own problems on its own with its own understanding of kinematics, dynamics, conditions of its motors, everything else. So when I talk about this problem in general, I like to talk about this in terms of constraint optimization. For those of you who aren't that familiar with it, I typically frame it like this, which is to minimize some objective function here, which has some penalty at the endpoint with some integrated cost, subject to some evolution of the dynamics of your environment model, some set of initial conditions, and some set of constraints on your input in your state space. So the problem with this is, this is often fairly infinite. This is also quite infinite. This can be, this can be expressed in any number of ways. You can have kinematic models, dynamic models, or approximate models of dynamics. You can assume everything is rigid bodies. You can assume everything is deformable. It's really kind of up to the person programming the system to try to figure out what is the appropriate representation. And the goal is to move away from this. How can you actually learn the models for how to solve this problem such that instead of explicitly coding what it means to have some evolutionary model of your state and hard code what the cost functions are that you may want, how do you actually come up with this on your own? So today I'm going to talk about the convergence of two areas of research that I've been working on in human-robot interaction and robot motion planning to a point where I'll get to, which is today, which is at the start of my lab here at the university. So a little bit of background on this. So I went to MIT about 2.5 years ago. I joined Nick Roy's robust robotics group, where there has been some historical work on generalized grounding graphs and published graphical models for language understanding. So I'm going to give a brief kind of overview of the nomenclature here, just so you can kind of get what's going on and point out some of the issues that kind of were existing when I arrived. So one way you can describe the problem of trying to come up with a natural language interface for a robot is to form this as a problem where you're trying to infer what is the most likely robot motion in the context of whatever language you are observing at a given time and some environment model that you observe. The tricky thing about this, of course, is your space of trajectories is quite large. It's the space of any possible future motion when you can move for an infinite amount of time. In practice, it's quite hard to represent that. I'll get into more of that later. So the first order thing you can do is you can build a simple graphical model, basically a factor graph, which has some representation or some random variable here which represents the language, the utterance that you express. And you have a correspondence variable here which measures the correlation effectively between language and whatever the grounding in this case, which in this case is a robot motion. You try to maximize the likelihood of this matching this through a true correspondence here. So that's effectively what this looks like. Maximize the likelihood of this true correspondence given your grounding, your language, and your environment model, which isn't explicitly in the graphical model here. So what we can do is we can basically transform the problem using things like log linear models so that we can learn feature weights for some set of known or programmed features such that we can maximize the correspondence here using techniques that some of you are probably already familiar with. Those who aren't, basically just amounts to maximizing the log likelihood of all of your training data such that you adjust your feature weights accordingly, and there's often a regularization term to make sure that your feature weights don't drive to infinity during the optimization process. So, so this is basically what it looks like. You have this function here where you're trying to maximize the product of this. So you have some sampling of your space of trajectories, and you look for the motion in the space of motions, which looks most likely to be in the green box and the blue crate. So which one of these basically looks like it? In the end, it ends up being X1. The problem here is you're evaluating the entire utterance itself. So it's actually kind of hard to come up with what are the right features for this model to learn that association itself. So one of the innovations, earlier on in that work in the generalized grounding graph before I got to MIT, was to assume conditional independence of each one of the constituents in some fairly primitive structure like a parse tree. We're not doing anything really as fancy as what James is doing quite yet, but I do want to talk to you later on tying this in. But anyways, so what you're doing here is you're trying to learn what is the maximum correspondence between all of these unknown groundings, assuming a true correspondence to any one of these bits of language where you're tying in basically the children of this parse tree. So when you try to understand what is the meaning of this noun phrase here, basically this and, you're bringing in the correspondences or what are the most likely groundings for this phrase and this phrase. So this is nice. So this dramatically improved your ability to learn these kinds of things. Basically, search goes as you basically have this big collection of objects. I view this as basically just a large bag of rigid objects in the world. So here there's actually about 40 different rigid objects in here, mostly because the PR2 model, which is the robot picture there in the middle, is actually composed of lots of rigid bodies, which all have their kind of explicit constraints, so all of their joints and everything else. So when we're actually trying to, well, I'll get into that better. Basically, you learn that the rigid body looks most like the blue crate, happens to be that object. You keep on searching basically from the leaves of the tree. You end up learning that and is the combination of those two, and you keep going. You search all the robot motions, and you find one that looks most like the activity, and you choose from that. So this technique has been applied in a number of areas quite well. So there was this autonomous forklift at MIT, which was using these generalized grounding graphs to take fairly straightforward assumptions like the power pipes on the truck and try to sample a set of motions in this fairly restricted space in order to get the robot to do this. And it worked quite well in practice for this example. The robot itself was quite interesting, fairly complex, lots and lots of LiDAR, lots of cameras. It actually did not require a separate microphone for the person to speak into, which was actually quite a bit of work to get that to work in practice in kind of outdoor, windy, noisy environments. But another area where this was done in is trying to learn something about maps when you walk a robot around. So can you actually try to learn an association of some expression like the kitchen is down the hall, or I'm at the gymnasium, or I'm at something else, and use this with all of the information you're building up to build this kind of hybrid semantic topological metric map. So it has been used in a number of areas, but when I got there, I noticed two kind of limitations for this. You have this exponential growth in the number of evaluations for sets. So when you have, when you're trying to figure out what is the truest something, when that something is the set of something, it grows as 2 to the n. So if you have a set of 10 objects, you have to evaluate 2 to the n combinations of that set to find which one is the truest. The second problem here is given its reference space of actions makes it difficult to generalize. So if I have a robot and I want to teach it something and I want to put it on a different robot, which has maybe a different schematic chain or a different set of physical characteristics or something else, how do I deal with that? And here's kind of a prime example. So pick up the hammer with the Kuka U-Bahn on the left and Will Graph here on the right. You kind of see that both of these are actually picking up a hammer in the sense that you are achieving force closure around a hammer and displacing it vertically from the table, and kind of the general ways you can describe a picking up activity. But the mapping from language to some set of robot motions or actual joint activities is wildly different between these two robots. I mean, the physical characteristics is dramatically different. So how do you deal with that? The way that I was pursuing when I got to MIT was this notion of constraint inference. And this actually ties into the problem that I was observing, which is inferring something about sets is quite difficult in practice using that kind of model. So we need to make a different set of assumptions when we try to learn language interfaces for this purpose. So again, revisiting my favorite set of equations, basically we're trying to learn this. We're trying to learn kind of the boundaries of your planning problem. There's a configuration space in the goal region that kind of defines the terminal condition that you want to achieve. All right, so constraints. So basically these are a whole bunch of very simple constraints like proximity, which is just being near something or being far from something, or contact constraints, which is actually a fairly high-dimensional function of whether or not two bodies interact or basically are on the surface of one another. This is a two-dimensional projection of one of the orientations, but you can imagine evolving the robot orientation and this actually looking quite different in practice. It actually looks like a twisted cylinder. But the idea here is you want to combine all these things so that you can take something like an expression, approach the blue box, and infer that you can effectively move around in this kind of dark gray region, go somewhere in this lighter gray region while avoiding contact with the objects, basically not sliding into these things, which is avoiding the white regions here. So, hard to do this using that kind of framework. If I just assume the constraints map to verbs in my environment, this is kind of difficult because of this problem that I mentioned about inferring something in the space of sets. So you have to sample what are the pertinent set of these constraints, or what are the relevant sets of these constraints that are valid for whatever the task is, and do your inference in that. So that's where we lead to this notion of distributed correspondence graphs, which is effectively an observation of you can reformulate the problem when you know several things. Well, I guess the main thing that you want to know is your space of things you can map language to is finite. So when you're interacting with something like a motion planner, there's a finite number of constraints you can hand to the motion planner such that it can actually work. So we're not mapping to this kind of larger infinite space, which could be any motion or any sort of constraints or any other things. So we can make an interesting observation here, which is that if you assume that the constraints themselves are conditionally independent, you can assume conditional independence of this model across the constituents of your constraint set, such that you evaluate each one of the constraints individually that could be expressed, and you figure out whether or not you should express it in your set, should not express it in your constraint set, or actually do something else, which is interesting, which is assume the inversion of it, which is important for constraints because often they are either in a space, outside of a space, or it doesn't matter whether you're in or outside the space. So that's actually what's expressed here is either you're in contact with that object, you're not in contact with that object, or it doesn't matter whether you run into that object at all. So this is this notion of your correspondence variable here is no longer binary, it's no longer true or false. It's actually any number of ways of expressing some known quantity, some known grounding, which in this sense are these constraints. So what this looks like in the simplest, simplest example where you're only doing this for verbs is you have this two-dimensional extrapolation of this model where you are assuming that you are still searching for true correspondences of your individual groundings, and you are searching for the unknown correspondences for a known set of constraints. Basically, the constraints can be handled by the individual planner. Now, you can do the exact same thing for objects as well. If you have a set of objects and you're trying to infer, whether something should or should not be in a set, you can do this as well. In this case, whether or not an object should exist or not exist in a set is often more of a binary correspondence, but imagine there's also ways to extend that to ternary correspondence as well. So this is what a distributed correspondence graph effectively looks like for moving the green box and the blue crate. So you have these, you have the same kind of structure that's dictated by the parse tree here, where in this case you're only searching over the unknown correspondences for a known set of constraints, which are dictated by the environment, your planner, and everything else you want your system to be able to handle. One caveat here is you don't have to have an equal number of groundings for every individual phrase. You can certainly do that, but if you want it to run faster for various reasons, and you can engineer out specific things like noun phrases will never map to constraints, or verbs will never map to objects, or something else, you can certainly do that. So mathematically, what this looks like is, the product over an unknown number of groundings transforms to a double product over the number of correspondences in your two-dimensional graph. And we search these graphs using beam search, much in the same way that we have done historically, because it's an efficient way to search the graph, and lots of very unlikely things basically exit the search process. So what this allows us to do is, use this in the context of, a robot trying to navigate through the world, and you can use it to infer more complex representations, like moving into the red box and the blue crate, where you have these overlapping, intersecting regions, which effectively say that, this command is only satisfiable when you end up landing in this region, which was not in training data. You just learn, effectively what it means to merge and overlap these individual relationships, and you can hand that off to the planner and let the planner actually figure out how to map, its own actions and its own degree of freedoms to satisfy these regions that you infer. So basically what it looks like in practice, you can just infer the relationships. You can hand it off to your favorite motion planner. Here we're using a bullet physics engine to model the underlying dynamics of the world, and we can generate this action. And we don't have to worry about how long the actions we're sampling or what the relationships are that we're trying to sample in, because that's all deferred until after we have language understood. So basically the kind of data the shape of the data that we hand to it is we take sample constraint sets and we generate motion plans for them, and we ask people to label the trajectories that they observe in the context of several different environments to generate a label for the constraint set. It's very hard to actually give people a whole set of equations and try to have somebody interpret what that means. So you give the meaning, you express the meaning of that through a robot in a world, through something like a motion or a video or something else. So, in this case, we had a whole bunch of people come in and they looked at a bunch of images and videos of these things, and people gave very simple expressions for these kind of activities. And we're looking at the computational complexity of this, and kind of as we expected, you have this exponential growth when you're trying to infer something about the set of the relationships using kind of the prior state of the art in the kind of statistical machine learning graphical model space, which was V-cubed, versus using the distributed correspondence graph, which you transform what is exponential number of true evaluations to a linear combination of the constituents. So you have this two-dimensional growth. So basically what this looks like is for 3 constraints here, you have 8 distinct regions, so you need to plan a motion in each one of these 8 regions. So that's how the comparison was done. And in a slide from my job talk, a year and a half ago, this is kind of the obvious pandering, rounding the phrase blue Rochester mugs. So the 2 mugs in the front. If you were trying to just evaluate what is the meaning of blue Rochester mugs, that individual noun phrase, you would have 2 to the 30 combinations, which is a billion model evaluations, versus the correspondence graph version, which is 30 factors times 2 correspondences included or excluded, which is 60. So, basically we're trying to address this whole scalability of graphical models in the context of language understanding. So you can do other fun things like add dynamics to your world model and realize that nothing has actually changed in the sense of the kind of relationships you want to satisfy. So it doesn't matter whether objects are flying around the world and bouncing off of other things. You're still just trying to satisfy some set of spatial relationships between objects. So, the motions themselves, all of these are approaching the blue box, and all of these environments look very different in the end, and the motions that actually satisfy these things look very different in the end. So it's much harder to actually try to learn something about the high-level activity or high-level motion of these things directly from looking at these videos that include the dynamics of the robot and the environment in it. But in terms of the constraints, they're all identical. And then you can do other fun things like learn a model for the Pair 2 and put it on something like the U-bot. This is a really simple navigation example, but basically you just try to learn something about trying to associate the root of your kinematic chain of this robot in proximity to that object, and you learn something about the root of the kinematic chain of this object in relationship to that. And that's effectively what was meant by navigate to whatever the object was. So open sourced this software package a little while ago. Google Code actually shut down, so now it's on GitHub. We need to put some updates to it. But very simple examples, data set. Basically, it's just a base for which to build a whole lot of applications which are interesting on it. So one of the things that I was doing was trying to map language to mobile robot navigation of this Husky robot when I was at MIT on this ARL program I worked on. It has a very rich command language on the order of 1 to 2 million constituents in that kind of set of relationships you can express. So here's something, swiftly walking through 3 red trucks in the left of the blue field instead of the right of the sidewalk. You're just trying to infer a representation of the problem you want to solve. You're not actually trying to directly solve it itself here. Basically, you hand this over to the motion planner its own definition of constraints and all the data set and everything else. In this case, it was actually running in about 5 seconds to actually compute this. I think we weren't running with the full 1 to 2 million constituents at this point as well. Getting that down to 5 seconds was actually quite a chore, but I'll talk about some improvements in efficiency in a few slides. Another fun thing we were doing is IKEA furniture assembly with a pair of robots. So here you have these 2 robots where this has a gripper and this has this little kind of interesting gripper hand spinner thing to basically screw table legs in. This is joint work with Ross Neffer, who was at MIT, now he's an assistant professor at Cornell. And in the end, you want the robot to, the pair of robots to perform a sequence of tasks and activities such that the table ends up looking like that. So what we can do is we can try to associate natural language with the preconditioned relationships in his ABPL language specification that he came out for this. Basically, it's a robot planning language which will automatically resolve any of the preconditioned relationships that are missing. Like if you say screw with table leg into the hole and it maps to this set of relationships, if you're not holding the table leg or there's something in the table leg, it will resolve all those things beforehand, so you don't have to explicitly lay out the entire sequence of activities at a very low level. You can talk to it at a high level of the planner and still map this. So it doesn't just have to be planning constraint that we map to, it can be any number of things. So that's just kind of what it looks like in the end. Other fun thing that I was doing with high school students at MIT was natural language interfaces for quadrotors. So, very simple here, go to the chair or fly over the box. You just give it a set of goals and it will fly around, and you no longer are using these kind of somewhat difficult to master joysticks for trying to get flying robots to go do things. Now you can just kind of talk to it and it will hover or follow or do any other things you may want it to do. All right, so you can do other interesting things with this, which is you can infer something about the maps in the expression itself by basically double dipping in language. So if I say something here like go to the hydrant behind a cone, and from the operator perspective, you can clearly see that there's a hydrant here, and you see there's a barrel or cone its way. From the robot's perspective, it may not actually be able to see the hydrant. So in its own perception model, the environment, it may not know what this is. So, kind of the default activity would be to blindly explore your unknown map, or whatever this hydrant is that I'm talking about. The other thing you can do is you can try to infer something about the map by trying to glean an observation based on that spatial relationship that we observe. So the fact that there's a hydrant behind a cone is something that you can learn something about the distribution of those 2 objects in the world model. And what you can do is you can generate a whole bunch of hypotheses about what that observation impact, or the modification of that observation on your world model, and integrate it out over all of your maps to figure out what you want the robot to do. So what this looks like is you have your utterance, you pop it into the natural language understanding framework, you glean out how might this actually change my map. Is there any pertinent or additional information you can feed into your mapping framework such that you can build a model of your environment or enrich the model of your environment with your perception sensors. Use that distribution of the maps back in language in the context of the utterance to actually figure out what you want the robot to do, basically generate your behaviors or constraints, hand that over to a MDP planning framework to reason about the uncertainty in the maps and the activities and get the robot to do things. So basically, it's this continuous loop. So this is a very simple version of what the world model looks like. So it knew that there was this cone and this robot was here, and it doesn't know anything about where the hydrant is. So you can infer something about the distribution of these objects, which is biased by the spatial relationship, behind in its own reference frame, to this kind of known thing that you're grounding to some physical object in the environment, and you get the robot to actually try to follow it, given that, and go ahead and plan. So here, we give it that expression. You go to the hydrant behind the cone, and you have the evolution of your map, effectively down here. This is joint work with some folks at CMU doing some of the motion planning. All right, so you can do other things here. Like this is actually an application on our smart wheelchair at MIT, which is a little bit more difficult from the environment in that there's a cone behind basically a bunch of trash cans, and initially when I say, go to effectively the columns behind the trash can, you have two trash cans, so you have two peaks in your map. So you try to plan given those two individual peaks. What you see in the video is actually it goes to the other peak, and when it discovers that there is not a cone in that location, that peak will descend and move into the other area. So it basically searches in a way which is more intelligent than you would certainly get if you were blindly exploring. There it is. And then it goes right to the cone. It's easy. We're actually using April tags here to basically feed in perception to make perception a little bit more deterministic, but there's no reason you couldn't fold this in with a normal object. So this is nice, but the problem with this is that as soon as you start wrapping this up to more complex environments and more complex constraints, even linear cost in terms of the number of things in your set becomes quite expensive in practice. So using the same principle of, can you learn something about your map? Can you learn something about the model that you actually want to solve this problem by doing a kind of high-level evaluation of your expression itself? So if I have this expression, pick up the mug on the plate to the left of the sink, and I have all this stuff in my environment, if I were to evaluate all of these spatial relationships and objects and regions and everything else that you have in here, you have 500,000 different things you need to evaluate. So you have clues from this in terms of the kind of spatial relationships you may need to consider by looking very briefly at the language and what's in it. So you mentioned there's a sink, you mentioned the spatial relationship on the left of, there's a plate, there's a mug, there's not words like, not or away from or anything else. So what you can do is you have this kind of two-dimensional representation of regions and objects, or spatial relationships and objects here when you're trying to figure out what your set of groundings or constituents you care about are. And what you can do is say, you can learn something about the expression of individual rules that allow you to express objects in the actual language understanding model itself. So, when I say on, that might indicate that above is something which is important, and left maps to that word right there. And the absence of a spatial relationship here basically means the object itself. So, in the actual meaning of this, you learn that these kind of things which are expressed are actually part of your model itself. So what it looks like here is you have another latent variable here, which is something about what the model looks like based on a set of rules that you infer, and you use that distribution of models that you infer are likely to give you a solution to effectively solve the problem for you. So what this looks like here is, you have something simple like pick up the mug. You have 39 different rules in this context, where rules are things like the spatial relationships, the object types, the kind of constraints that you may want to satisfy, and basically you learn some subset of rules or some set of groundings by the expression of these rules that allow you to vary the number of groundings you need to evaluate in your language understanding grounding model. So here, instead of assuming you have 2,500 groundings per phrase, which you would normally always use, you can have 0 to 2,500. And for simple expressions, often these are very sparse in terms of the number of things that are actually positively expressed. So what we observed in a workshop paper in 2014 was basically this order of magnitude improvement in the speed by trying to learn something about the model and taking that penalty of stopping to think, what is the right model for which I want to use this that will not cause my inference to be inexact, or not exact, because you're still reasoning about the uncertainty of the model. But what is the most likely model that will actually allow me to solve the problem and give me good results? So more recently, this was submitted paper to AROS. This is looking at the relative efficiency of the various different types of models where G-cube is this exponential thing that I showed effectively earlier, and the DCG model has a linear growth. Basically, what we're observing here is as the model becomes sufficiently complex, as the number of groundings you have becomes significant, actually gets quite a significant growth in the difference between the performance of those two models when you have this relatively sparse set of relationships. And we saw basically no difference between, effectively no difference between the accuracy of these things with kind of the uncertainty that students were using this. So, given that we now have a more efficient way of inferring some of these relationships, we can now enhance our language understanding models for direction following to include spatial relationships. So, go to the kitchen that is down the hallway. We're doing language grounding again. We're double-digit language to infer something about, the kind of spatial relationships and everything else that exist in our world model, and then again double dipping our behavior in the context of all of the maps that we infer to figure out what the robot can do. This is effectively what it more or less looks like in the beginning, where you have this kind of known region and kind of this wider distribution, but generally in the right direction, and it all kind of converges as your sensor information goes. So that's what it actually looks like. This is for a paper we're presenting at ICRA 2015 in May this year. It just goes over the basics of it. So we do make this assumption that we are using some sort of parser here. And right now we assume a very simplistic deterministic parser, but there's not a reason why we couldn't use a richer parser or a distribution of the parses in the context of this. We just have to reason about that uncertainty and effectively integrate that out if we were to extend this. What's actually interesting is initially we were using things like the Stanford parser, which is trained on things like the Wall Street Journal corpus to use this. But a lot of the expressions and a lot of the things which are very likely for reading something like the Wall Street Journal do not necessarily map well to the kind of structures you observe in robot activities or robot commanding. So, probably about 6 months into my postdoc at MIT, I decided to just start rolling my own training myself. All right, so now I'm going to divert. So now, I've talked about that first arc, which is all about how to learn some about specification and learn some about the model that you're actually planning in. I'm going to talk, very briefly about motion planning before I get into what I'm up to here. So revisiting kind of my favorite function here. It's basically a robot motion planning. Effectively boils down to actually trying to satisfy this while making some assumptions of what is the distribution of actions and what is the distribution of states in your world model. And the kind of things that I typically talk about when I talk about robot motion planning are optimality, efficiency, feasibility. So optimality is the degree or the quality of the motions that you end up resulting with as a function of whatever your decision-making process is. Efficiency is the complexity of the model itself to make that decision. And feasibility is the degree to which your solution maps to reality. So I can certainly assume the entire world is two-dimensional, and I can walk across campus and that's perfectly fine. But that activity may not reflect anything close to reality. And in hopefully a year or two, when we have this nice new building being constructed, if I just assume that I use Google Maps to do this, I will probably be wrong as the fastest way to go across campus. So two things that are kind of important to some of this work that I've sort of worked on is this differentiation between global motion planning and local motion planning. Hard motion planners basically are designed such that they use high fidelity models at the nearby the robot to ensure safety, feasibility, and progress towards a goal, whereas you degrade the fidelity in the global scale to try to get guidance fairly quickly, and you don't have to discard all this kind of deep understanding about your way your robot may move through an environment that you haven't even seen yet. So talk quickly about trajectory generation, which is actually one of the first things I did as a PhD student, was working on this problem of how do you get the robot to simply go to any other space subject to some kind of uncertain, or not even uncertain, some kind of unknown forward model. So this is effectively done efficiently by trying to parameterize your input space. So you assume that your space of motions is not the space of all motions. It's subject to some set of fine control parameters, and you invert this model numerically based on forward or central differences of your predicted motion model to generate your parameter updates. So this transform was a problem which was generally quite slow because you had lots of not points, and sometimes encoded things which are very specific about the way your robot would actually plan to move through the space in a way that you can actually do whatever you want with your forward model, and the algorithm would naturally fly. So a very simple example here was this planetary rover that I did a lot of work on later that I'll talk about, where we want to satisfy going to some particular pose, and you have a set of level, basically 0 error conditions for your X and Y pose, and these 0 degrees of freedom you're actually trying to resolve for. Basically just follows gradients and gets to a point where you're actually on the zeros of those two individual global curves. So Of that. So you can do interesting things here, which are you can build locomotion planning graphs which encode something about the kind of dynamic or kinematic constraints of the robot itself, and you can map these subject to whatever initial conditions you have very quickly, because the optimization process itself is quite quick. So if you have this two-level locomotion planning graph and you have some set of initial conditions where the robot happens to be turning to the left, your initial ring of motions actually looks quite a bit different. So it just is a function of updating this space while keeping the outer space, and you can do other fun things like adjust this to work on non-level terrain. So you take kind of the two-dimensional approximation of the world and simply update your parameters, use them effectively as initial guesses to give yourself a much better understanding of the way your robot will drive and make decisions through this world very quickly, because you're using a very small number of parameters to do this. You do other fun things like compare your mobility model. So here is a planetary rover I worked on at JPL circa 2008 when I ran some of the experiments. But we drive forward to this rock, and we want to go back and do this where we actually turn off that right view. But the motion planner doesn't know anything about it at this point, so it just moves, and basically it operates in a way which is suboptimal, and you would need to rely on feedback control and hybrid state estimation and everything else to fix this. Or you can just tweak something about the input model that you're using and actually predictably compensate for that disturbance in your motion model without adjusting your space parameters or anything else. It's just a matter of, if I know that I move forward with this space of the inputs, I know I'll move in some sort of suboptimal way numerically, and that gradient, the space of gradients will actually change. The level curves will basically shift such that you actually get to the right spot subject to whatever that model disturbance is. So you can do other fun things like build locomotion planning search spaces which are subject to environmental constraints and start biasing some local information. So when I got there to CMU, kind of the state of the art of what they were using for local navigation for these things was to sample input space and simulate the motion such that they were all feasible in the sense that they used a high performance model, but they didn't have a lot of control over where they went in state space. So if you have a way to basically sample a set of constraints and very quickly generate a motion such that you can move in that direction, you can actually be much smarter about the way you build these graphical models to ensure separation between individual candidate motions. And you can do other fun things like if you know that this is a kind of low cost region and cost increase generally here, you don't have to sample uniformly in the space of relationships. You can actually bias your search. And in the context of autonomous automobiles, you can actually sample the space of environmental constraints so that if you want to keep your robot effectively driving in the road along the length of the road, you can sample only those kinds of relationships, so you're not doing a wide search where 90% of these things are automatically off the road. So here are two robots that actually apply those two techniques too. On the left is Crusher, it's this very big field robot, and on the right is Boss. This is the DARPA Urban Challenge vehicle when I was there at CMU. So, in both of these cases, the underlying trajectory planner is identical. It's just a variation in the predictive model that each one of these are using, and a difference in the way that you're sampling, subject to the fact that on the right, you have lots of environmental constraints that are defined well by the road, and on the left, you have a much looser set of constraints, which are effectively just dictated by your sensing map. So you don't want to, in this case, drive into one of the containers, so you can remove the samples from your local search space, but that's a very strong function of that kind of navigation and kind of loose, poorly defined environments. This is actually fun. This is the first test about 25 miles an hour sitting in the back with a fairly jumpy camera. But there's nothing in here that was special about obstacle avoidance maneuvers or anything else. It was just that we had a well separated enough search space because we were smart when we were sampling our relationships. Was the work. And this is actually the importance of having a good predictive model during the race day, which was that we knew that it actually took a while to turn the wheel, and we knew that there was something effectively coming at us. So we started turning well in advance of that. Whereas if we had just assumed a geometric path and assumed that our path following controller could follow it, we would have almost certainly slammed into that vehicle and not collected the prize. So other fun extensions to this, when I got to JPL post-PhD, I worked on a robot manipulation program called the DARPA ARM program, where we were trying to do a whole bunch of manipulation and grasping tasks with this one-armed robot. And this notion of having a parametric approximation of your input space and sampling the space of constraints applied, actually quite well for these 15-degree freedom systems. So, here we have, the robot trying to pick up the flashlight, night light thing, which it observes here, and pick it up and put it on this piece of orange paper over here, and then returns its condition. So, what's actually kind of interesting here is there's a whole bunch of assumptions in this model about, we assume that things which are not kind of named objects are bounding boxes, and we assume that there's kind of a flat table here. And there's lots of other kind of interesting assumptions that are built into this planner that I'll talk about a little bit in future work that I'm trying to move away from research. But it was a very successful program. We got the robot to do lots of fun things, including one of my favorite ones, which was actually picking up a drill and drilling a hole with a block of wood on a tiny little red dot you can see there. That and this task was actually the hardest. Picking up, and not just because the robot had no idea what a phone was, because I've never seen one, but there's such a small clearance between the sides of the phone and putting up on the thing that it mounts to, that actually getting that to work properly was quite a work. All right, so one of the last things we're going to talk about in robot motion planning is this notion of adaptivity and state lattices. So state lattices are one of the ways that you can generate a motion plan through one of these environments, which basically involves deciding on some local trajectory library, which then you copy through an environment repeatedly, such that you don't have to constantly reevaluate the trajectories themselves when you expand this lattice. So feasibility, according to whatever model you assume beforehand, is naturally encoded in whatever the space is. So this is great if you kind of know what your environment looks like, and I think this is MSL landing 2013 era. So if your environment kind of looks like this, it's great because everything's not really flat, there aren't obstacles, and just kind of looks okay. But later on, they ended up in Bingo Gap, which is kind of a funny spot. But it's actually a much more complex environment. You have this interesting dune, and you have a lot more complexity in the environment. So if you assume that you're going to be navigating in the prior space, but you end up landing in this space, or you end up driving through something like this, and you basically need a way to revisit your assumptions or adapt your assumptions subject to the complexity of the environment that you have. So what this kind of looks like is, on the top you have this notion of graph, which is edges and nodes in a graph. On the bottom is the mapping to states and trajectories, basically the actual physical locations. And the idea here is to try to adapt that mapping locally based on observations or cost functions that you can observe. So what this looks like here, is if you have these kind of control points in your node, and you can relax the way that this maps in terms of the position orientation, you can do things which modify that assumption and use things like the trajectory generator I talked before to ensure feasibility in this graph. You can do things which actually move it into this region based on the aggregate cost of your local connectivity. So you can do things which again look like this interior optimization step where you kind of move everything along this gradient of cost such that you land your nodes in a better configuration. So this actually involves looking ahead during the expansion of nodes in your open list to figure out where they should land based on, again, the adaptation of your future connectivity, such that if you thought you were going to land here, your updated configuration actually starts shifting them off based on their own individual orientations. So what this looks like is, this is kind of the solution you get out of a coarse fixed graph, which, it's okay. It finds a solution. It's not really optimal. But then you hand off the same lattice to something which can adapt and basically learn something about the way it should move through the environment without actually changing the topology or the out degree or anything about the node itself, and generating a much more efficient path. So this adaptivity costs something. So it's interesting to actually look to see, as your environment becomes more complex, is it actually better to adapt kind of a coarse representation or simply replan with a much denser representation? So, as we added more obstacles, the difference between these solutions actually became much more dramatic. That's kind of a coarse fixed. That's the solution you get out of the coarse adaptive, which actually mapped, basically the solution by this higher representation. So what was found in some of these things was, the coarse adaptive solution here was actually faster, shorter, and used a lot less memory because there were a lot fewer nodes on your open and closed list doing this from the search. That was actually better in many circumstances to be, simply smart and adjust the way that you actually move through this environment as opposed to just sample, kind of brute force, add things to your search process. And this is actually particularly important for systems which have limited memory. You know, things like quad rotors, things like planetary rovers, things which are kind of sent out in the field, and you know, they don't expect kind of a doting PhD following it around and it doesn't sound fly. So this is actually a trend that followed to a whole lot of experiments, which basically found as the environment became sufficiently complex, your the cost of adaptation was very quickly overcome by the relative improvements in efficiency. You can do other fun things like update your adaptation subsequently. So basically, you only iterate or you only optimize a little bit every time you replan, and which makes sense for doing this kind of mobile robot navigation, where further closer to your goal, your notion of your cost may actually evolve as you go. So it doesn't actually make sense to do full adaptation every time. You just suffer a small penalty at the beginning and throughout. So last thing I'll talk about is this notion of predictive motion models, which is this idea of what is this right model that you want to choose at any given time. So if I have something like a robot here, this is actually a here in 2014, where you're simply sampling something about the local elevation map here, and you're looking at the difference in the solutions of 4 individual models, where the very simplistic kinematic two-dimensional model is up here, and the full dynamic model with nice wheel slip and everything else is evaluated down there. How to actually choose the right model based on trying to balance this notion of computational complexity and relative accuracy. Basically, it's accuracy measured to the most complex or most detailed model. So what we actually found is we can learn a neural network, we learn the weights for a neural network such that we can automatically adapt between these two things, such that if we have these road networks and we have different variations of the model, and red is kind of the higher fidelity model for the rough terrain, and green are the basically switching points where you assume kind of a plainer, simpler two-dimensional model, that now this kind of a priori assumption about I think my robot will assume or view the world as three-dimensional, or it will assume that it views it as two-dimensional, is no longer fixed. It's simply learned online, or learned from lots and lots of data that you can run offline, and then applied in online navigation. So I finally made it to now. So we're starting up this new laboratory here. So the high-level mission is this notion of trying to investigate algorithm models for robot intelligence, human-robot interaction, to make an impact in lots of fields. So we have our temporary space over in Open here. It's kind of closet there, which is fine, but soon we'll be opening up the Gavit lab. I actually hope to go pick up the keys this afternoon to it. But all of that stuff will hopefully be moving out there. It's actually been a fairly exciting week in terms of getting things up and going in the lab. We got our Baxter robot up and moving and doing other things. Our Husky robot was delivered, but it's still in boxes. We don't have room to unpack it. We have 5 turtlebots now, and my daughter came on Sunday. So now I guess 6 new robots in 1 week and 1 new daughter. So a few things we're going to be doing with these things is, we have this pending task which we can get started on modeling and verification of language-based interactions. So if you have these, language interaction systems, how do you actually, instead of just saying, I'm going to infer some set of constraints and I assume that, it will work, how do you actually learn something which is, how do you actually infer some relationships and question whether or not the robot can actually do it at a very high level? So, so this is actually about trying to map language to something like linear temporal logic, or something else about learning something about the spatial relationship between different objects. So, so we're actually using Baxter for this purpose. So this is a movie actually we shot this morning. So this is Jake Arkin. This is my PhD student from ECE. This is going to be the platform that we're going to be using for some of this work here. And one of the ideas is actually trying to do things like learn LTL expressions for a whole bunch of individual manipulation activities, and learn kind of the individual expressions right now. Historically, or not historically, what I've talked about so far is always understanding of a single expression, a single sentence. But now I want to move to conversations where I want to say, pick up the coffee cup by their handles, do something more than 5 minutes force, and then do the coffee cup behind the family reference. So there's lots of things that are actually really hard about this, including how do you resolve metric relationships in here? How do you express that to a planner? How do you remember that? How do you actually merge all of that information in some kind of higher level, conversational level understanding up here? and then not only figure out what it is you're trying to do, but something about the model you actually wanted to use to solve. Another activity we're trying to get up and going is this institute monologue comprehension for faster mission tempo, which is about this idea of trying to express something about your world model to a robot here. This is actually basically a version of the Husky, which is sitting in that box over but this is me out at a field test trying to get the robot to drive around just by talking to it. One or two other fun things is this notion of probabilistic adaptive state lattices and tying in language to this. So, before I always just assume that we will apply adaptation with a certain number of steps, or apply until basically your gradient roughly approaches zero. But if I relax that assumption that I'm always going to apply adaptation, can you actually learn something about whether or not you should adapt, the way you should adapt, or the way you should actually even modify your control set or directory library in a given environment such that you don't waste computation. So if you look at the kind of distribution of samples, basically you have these kind of loose clusters, which implies there's a lot of relaxation, which is the relatively open spaces where all the nodes haven't moved. If you were to simply ask the question and possibly try to learn a model which says, I'm in a relatively open space and I learned that, applying adaptation basically effectively means a level cost function, so there's no point in actually applying that. I actually think that's quite a bit faster than just trying to apply adaptation uniformly and letting that go. And the other part here is tying in language to this. So, again, this is robot motion planning and or completely outside of the kind of human guidance that is available in a human robot cooperation task. Actually using language to impact the way that a robot makes a decision and the representation it uses to make a decision is, I think, actually one of the things we're going to be exploring first in the laboratory itself. And this goes to this notion of, can you use language to basically provide hints about how it should be solving it, or the way you should distribute samples in your world to perform tasks more effectively. One or two other fun things is these multimodal graphical models for HRI. So, right now I'm just kind of using very simple parse trees for this purpose, but can you use richer models like we talked about before, or can you use something about the inflection or gestures or any of these other things to actually impact what you're talking about? So if you talk with your hands, like I've been doing most of the talk, that may actually have some meaning in it in certain contexts. And actually trying to learn something about models for directory optimization by employing the same conditional independence assumption about your graphical models that you use for language, actually tying that back into planning, where you can learn something about the way you set up a planner for some generalized robot and how those design parameters evolve over time as you apply characteristics of robot models and environment models. So that if you have a robot and you set it out during the summer, it may nominally want to plan activities a little bit different than it might in winter, because slip models are more important when it's wet out. And, maybe you want to avoid the sun or be in the sun, for solar incidents if you have a solar panel driven robot for that circumstance. So, all right. So I talked about a lot of stuff. I'm going to wrap up now. I think it's quite exciting that we get to start a laboratory here doing these kinds of things that are focusing on trying to apply, model learning for robot decision making, and really is kind of this interesting confluence of how do you absorb the kind of expertise of the person in these cooperative tasks and apply and learn something about the way the robot should make decisions itself. So thanks for your attention.
I'm wondering if the relationship between action modeling and language can be inverted so that the robot will be able to say what it did. So when it has been directed to the orange cone or something, it says, well, I went to the blue box and the cone wasn't there, and then I went to the other blue box, things like that.
That's right. So well, I guess it actually ties in two things. One is the whole human-robot dialogue thing, where you send a robot into a building and it comes back, and you're actually, so the robot actually has a much richer environmental model than the person does. So you actually try to do exactly what you said, which is reason about the spatial relationships that it has in its map, and try to generate a whole bunch of facts that you can then try to express back to the person. So that's actually something which is kind of related to one of the things that we were looking into doing for the little robot navigation task, but I didn't mention it. But the other thing is this notion of what is it? The visibility. Basically, trying to glean intent from robot motions is actually kind of an interesting topic these days. So whether or not you can actually observe what a robot is doing by moving very deliberately in a way which is suboptimal for the robot, but looks much more like a human motion is something that a lot of people are starting to look into, which is independent from language. It's just purely the robot swinging its arms and moving around. Is the person going to be confused about what's going on if they're not deeply in tune with how the robot motion planner is programmed? I actually observed this directly on that robot manipulation task I worked on because I was purely trying to minimize for time. So I'd always pick up something, and I was very confident in the kind of models and things we're using. So I'd pick up something and I would swing it really fast by the table, and it wouldn't hit the table because my controller worked and we had a good model environment and else. But it definitely disturbed all the program managers that were watching. Every time that people didn't make that, every time that didn't work, they ended up slamming at the table and breaking fingers. So, but yeah, so observability or trying to communicate intent of both physical motion and actually trying to invert language models is something really useful to do. Yeah.
Well, that brings up the case that if you're trying to communicate with a robot using language, that kind of presumes, in many, if not most use cases, you're going to have human beings in the workspace. And so, I mean, have you given any thought to how you're going to incorporate like something functionally equivalent to Asimov's laws of robotics into your planner? So that, no, seriously. Yeah. I mean, 25 years ago, I worked on at Boeing on a Honeywell gantry, and the robot arms in there were ripped in half, and they were looking to take this double-sided sticky tape and place it to make composite material, and people were in that, in their plans, in their dreams. But I mean, things like proximity sensors and all that stuff, or what does shall not harm? Is that a 5 nines task, or
So what? The interesting way I think it would map with the correspondence graph that I was talking about is you have a set of relationships which is always true. So independent of language. So you basically would learn something about features, which is, if I say any words, I need to apply this set of rules or this set of relationships that I want to satisfy. So you can actually learn effectively the hard-coded safety constraints in that model. So no matter what I say, I will always express those things.
How do you define what harm means? I was going to ask earlier.
Oh, that is a much deeper question.
How do you define what near means?
So because we use humans to do the annotation here, we simply rely on the quality of the data that we hand to them and the attention of the annotators themselves. So we don't explicitly hard code an assumption about what is close or what is far, or what is on top of or anything else. We simply ask people to kind of make their decision on what they think that is, and hopefully with enough data you would learn something about what that association is. But yeah, it would be nice not to have to assume something like 1 meter is close to something.
I mean, not to go FDA on you, but before this goes out there, right? I'm going to want that answer.
That's right. Yeah. Well, again, the question there is, if it's a matter of not harming people, I think those things are universally true. So learning those kinds of concepts are much easier than things which are semi-ambiguous, like being close to something, driving near something. So that actually ties into some of the metric relationships right there, right? So you can be really exact about how close you want to be to something. As long as you can fold that into your representation, you can be very exact, or you can be kind of loose and coarse with it, which is just go by that, or go near that, or go take a look, or something else. It's not something like examine every inch of something, or be 3.5 meters from that object, or apply 3 pounds of force on something. So you can be really detailed with the kind of, but right now it's kind of confined to kind of simple core spatial relationships. But I think the framework would extend.
With people, it's a little more exceptional. You could break a crate and people that, but you break a person, that's less forgivable.
Oh yeah. I think that's. I believe that is generally true for the difficulty with all human robots. Fortunately, with the Baxter robot we have here, it's actually designed for working collaboratively with humans in that it has a bunch of safety things built in. So even if the robot is doing something which is not smart, it will detect collisions and stop moving. It's designed to be human safe. And you actually see this trend of people trying to design human safe robots, such that when you can share a workspace and you don't have to worry about those kinds of things. Because they're not always going to be people with PhDs following these things. They should be usable by everyone. Questions? Yeah.
I noticed movements were fairly jerky. I assume that's a matter of computational power.
Which one?
Oh, for many of the robots, when they were planning, for example, the wheelchairs and other stuff, as they were moving, they would stop, and many of the videos you showed were sped up.
That's right.
So my question is, looking forward in terms of processing power, what is the bottleneck to having real-time motion control?
So often the jerkiness was not actually the decision making. Often it was actually trying to build the map and reason about the uncertainty in the map. So so part of that, I guess, still is planning, but like in the wheelchair case, it would actually scan and it would try to build this new distribution of maps, and that was actually the bottleneck in that case. It wasn't the decision making. But things like the autonomous automobiles and other things, those were doing real time trajectory planning at 10 or 20 hertz, and that was done by trying to throttle the sampling such that you can do that within its kind of window of space. There's anytime planning techniques that will actually assume a very suboptimal, basically assume a inadmissible heuristic to speed up your search, and with whatever time you have left over, you can iterate and improve on your solution within some kind of proven bounds of optimality. So you can do things to try to get that real-time performance, but in many of the circumstances, at least for some of the things that we're worried about, we didn't need kind of continuous motion or real-time performance of the entire architecture. It's okay to sit and wait and scan. For perception sensors, it often works better to be stationary. You don't have to worry about blur and other things as well. So, but I mean, in general, a lot of the work that I worked on when I was at GPL doing potential local navigation was trying to speed up the autonav process such that you were continuously moving. So you weren't following this pattern of you kind of drive somewhere, you sit there with the cameras, and you look around for a while, and you'll take a map and you keep going. We did a paper in 2012 on trying to port over parts of the slow parts of the pipeline into FPGAs to speed that up dramatically. I think it was like a 2-order magnitude improvement in the speed of stereo and Visodom by putting it on FPGAs. It's a lot of work to put on FPGAs, so you want to do it with your algorithms, but you can use different architectures to speed up things if they are particularly amenable to that. So there you've got lots and lots of parallel processing things, so FPGAs worked out well for that.
I would imagine, for example, with the quadcopter, a lot of the quadcopter experiments, they're done in rooms, the rooms have cameras, all the processing is done outside of the vehicle. But ultimately, I think you'd want the quadcopter to be able to take pictures and not just have to stop and hover every time it needs to figure out where it's going.
Yeah, there are examples of people doing purely onboard quadcopter navigation. I think a few of the higher level quadcopter organization things actually have competitions every year on trying to do that. You send it into a building, hopefully it comes back out. So there is push and there is motivation towards that. And part of that really is in trying to figure out what is kind of the minimum model that will actually get you the right solution without wasting computation, which ties very closely into these kinds of ideas, which is you learn how to solve the problem instead of just applying kind of the I don't want to call it art in the sense that basically applying your own experience to what works well or applying techniques that have worked well for other roles. So
I guess another way to say it is continually update your desired path as you go instead of doing the iterative stop, plan, stop.
That happens a lot in practice. Basically, it's that idea of you have a global cost function. You have a global navigation function that you're trying to follow, and that will adjust automatically. So that's actually that difference between local navigation and global navigation. So your global navigation will update at a much lower rate, whereas your local navigation will make sure you don't slam into this. So questions?
So I was just wondering what's within your immediate future purview in terms of the expressivity of planning language and corresponding natural language, thinking of things like collaborative action, iterative action, picking up all of the hardware that's been spoken before, conditional action, when you see a person, offer them a donut, that kind of thing.
So conditional actions are quite interesting in that I don't think we can uniformly apply the conditional independence assumptions that I'm using in some of the correspondence graphs. So even that assumption about, I assume that the constituents are independent is actually something I want to learn whether or not I want to express or not. So it's this kind of interesting trend of, I assume that everything was not conditionally independent in the beginning. I moved to assuming everything was conditionally independent independent to get a speed improvement, but somewhere in the middle there is actually where I want to lie, where I do actually need to evaluate combinations of things to reason about things like while and if or some of these other things. So I think there's still quite a bit more work to be done on the language understanding models and the framework for building the graphical models to do that. In terms of the kind of more direct applications, we're looking a lot more into manipulation. So how do you actually express how one of these robots should pick up an object or screw one object into another object or stack objects? So there's a lot richer language that than what I've been using historically on focused mostly with mobile robot navigation that you need to reason about. And it might just be it's a higher dimensional space because it's the entire pose of the objects you're manipulating.
I was wondering, for instance, in the case of the furniture assembly robots, whether they were collaborating in a strong sense, one holding the table and the other to keep it from turning while the other one screws in the way. So
they were, but they were hard coded to do that from the ABPL timing language that Lost Temple was working on. So here we come up with these preconditioned relationships, and you hand them off to the planner, and the robots would jointly plan because it was actually the case where screwing in or placing one of the tables, I think the one robot would go kind of hold the object here while the other one puts the other surface on, and then it would let go. So there was that kind of cooperative action that was dictated at a very high level by those relationships, but we weren't actually using language to build that set of rules relationships, which I think would be quite interesting. Any other questions? Yeah.
How big was the training data for upright task?
For that one?
Yeah.
A couple hundred examples, a couple hundred labeled examples, but the interesting thing with the training data there is that for every labeled example, you have a whole lot of these. You have a whole lot of these factors. So when you have one fully labeled example here, which is some expression given in some set of relationships here, you actually have the product of these factors times these factors in terms of training data to actually train the local models. So whereas before we had to explicitly provide negative and positive training data, here you know what all the correspondence values are as long as you know n-1 number of their values. So. It's unexpected, but okay.
Talk with it.
I don't know if that's right, so I'm going to leave it. Any other questions? All right.
Thank you.